Well, good afternoon, everyone, and welcome to week 5 of your technical lecture series. As you know now, I always start with this branching system just to kind of contextualize where we are. We looked over the last couple of weeks at this area here, what we call structural elements, the bits and pieces that go together to make buildings. Specifically bearing elements or components, if you like, that take load to ground, and spanning elements, platforms, bridges, floors, whatever you would like to call them. What we didn't do, and this is really a note to myself, was look at this little area here, which is connections and joints, but we'll probably do it when we look at materials technology next term. So we're going to move on to the if you like, the coming together, the final part of this section on structure and form that we call structural logic. You might call it structural systems. Nevertheless, it's the different ways in which these elements can be combined to make structural form, to make three-dimensional structural form. And you'll see, as in many of the things that we do, again, that there are two major subcategories in this section on structural logic that we call compressive structures and tensile structures. Now, you already know what that means fundamentally, because we've looked at structural physics, and you are beginning to understand the difference between tension and compression, I hope. And again, these areas are then subdivided into in each case two major categories, which is two-dimensional shapes and three-dimensional surfaces. It'll become clear why these subdivisions exist as we delve into the subject. So, structural logic, or systems if you prefer, goes back to what we were looking at previously, which is the various elements that combine together to make three-dimensional form. And structural elements can be recombined, should we say, in any number of ways to generate form. But there are two geometric types that we classify. And one is looking at two-dimensional primary shapes, and the second is looking at rather more complex three-dimensional shapes, from which you can only really understand them from their surface geometry rather than from two-dimensional primary shapes. Now, let's have a look at this chart. I will put this on your Blackboard site so that you can again pin it up on your wall and have it in front of you to look at whenever you need to. So go back. This is the principle of structural logic here. We are applying geometric procedures to two-dimensional primary shapes. Now, these primary shapes are all structural shapes, aren't they? Look along the top. Two-dimensional shapes. Very simple post and beam. Some of you will call it a goalpost structure. An A-frame. You'll see many buildings that take that shape and form. A portal frame, an arch, and a cable stay. Just to go back, so the portal frame is actually a combination of the post and beam and an A-frame, because what you will notice immediately about a post and beam structure is that it's not braced, is it? There is no bracing inherent to it. The A-frame is inherently braced, of course, isn't it? Because it's already triangulated, and there's an element here which is connecting the two triangles. The portal frame, which is a very common way of putting structures together, combines the two. So you can just about see here, there are triangulated sections that make up the excuse me, that was me coughing, that make up the goalpost. The arch, which we will go into, which is a critical development in structural form, and the cable stay, the reason it's here is because you can see from the diagram the cable stay involves some elements that are in pure tension. These are all in pretty much pure compression, although the A-frame, to be fair, this element here might be in pure tension because it's just stopping the two legs splaying away, isn't it? Kind of as I say, the cable stay has elements that are in pure tension. So what we're looking at today is two-dimensional primary shapes. These primary shapes are will contain an area, won't they? And the moment you apply, as we say here, by iteration, certain geometric procedures, such as, very simply, extrusion or rotation, by repeating that element in either of these ways, you begin to develop three-dimensional forms from the repetition or the iteration of the two-dimensional shapes. It is fairly simple when you look at it that way. So, if you extrude a goalpost, you will get a very simple post and beam structure, such as this. If you rotate the goalpost, you will get another fairly simple, post and beam structure. If you extrude the A-frame, you begin to develop volumes. If you rotate the A-frame, you actually develop some really quite interesting volumes, such as the tetrahedron, the pyramid, and if you keep going, you'll get to a cone, won't you? Similar things develop with portal frames. Now, the arch, which we will go into in a little bit of detail, actually can develop in all sorts of ways just by applying these simple geometric procedures. So if you iterate an arch by extrusion, you will develop what is commonly known as a barrel vault. If you extrude the arch but you offset the barrel vault, i.e. instead of making them parallel and orthogonal to each other, you set them at 45 degrees, you develop an offset barrel vault. What is the advantage of this? Well, you probably know already, don't you? Because you're sort of already triangulating the structure. So you avoid the need here to connect the arches, don't you? You're triangulating it, so it's a self-bracing structure, the offset barrel. When you start crashing, if you like, barrel vaults together, orthogonally to each other, suddenly all sorts of interesting geometries open up. Specifically, or traditionally, the groin vault. That's the groin. That little mark there, that is the groin of the two vaults meeting each other. And at that center point, if you have four vaults meeting, you develop these rather beautiful geometric shapes. By rotating arch structures, things really do get interesting. Particularly when you look at traditional sort of Gothic low tensile architecture, stone cathedrals and the like. By rotating the arch, you can develop diamond vaults, stellar vaults, and domes of one sort or another. Similar procedures can be applied to the cable stay structure. These are more modern structures because the ability to produce, shall we say, elements that can operate in pure tension, rope and wire, are relative. Rope is not a modern development, but wire rope, steel rope, which you can take an awful lot of load, is a relatively modern development. Hence we get beautiful buildings like this, the Schlumberger Center by Hopkins Architects, and we of course get what you call the O2 Arena. I call it the Millennium Dome still, but there you go. By rotating a series of cable net structures. Look at what's happening here. We've got a series of cable net bridges, effectively. Oh, haven't we? One, two, whoops, beg your pardon. Anyway, let's move on. So here's a simple post and beam structure. You'll note here the perforated beams doing the long spans. That's what, 8-10 meters probably. You'll note these are not I sections, are they? But they're square section columns carrying the loads to ground. This is nice because what you're seeing here is this is a rotated post and beam structure. The structure, as you know, we quite like is on the outside of the building, so you can see very clearly the logic of what's going on here. These are the elements. This is what's carrying the floors. So that's the depth of the floor. That's the spanning element that meets in the middle by rotating there's the columns that are carrying the loads to ground. Here's the spanning elements. Here is a little Vierendeel truss, if you remember, that is just bracing each of those columns that are rotated on plan. There's a kind of similar thing going on with bamboo, a material that is very interesting. Apparently it's a kind of grass, according to my son, but it's timber. I think it's a softwood timber, but it's a kind of grass. And it's being more and more commonly used because, of course, it is a sustainable building material. Here's the same logic applied with very delicate steel trusses extruded to create volume. If you go back a little bit and think, okay, in most of these cases we are just carrying loads in a kind of fairly traditional manner. You can hang loads. So this is Mies van der Rohe again. This is Mies. Look, here's the columns. Here is the beam. So it's a post and beam structure again. Instead of sitting the roof on top there, the whole structure is actually being hung from this series of goalposts, which is again rather elegant. Elegant because you can see the structural logic clearly. That's a big girder, isn't it? It's it's a solid web with a little bit of reinforcing for that part there. And there we go again, same idea. The floors are being hung from a series of goalposts. As I say, I like this because it's very clear understanding of the structural logic of the building. These are a series of bridges in pure compression. The floors are hung from these bridges. They're the same thing happening again. Interesting building, the ICT Media Center, which ICT Media Center, look it up if you want to, if you have a look at it. Here it's really clever, very obvious, isn't it? Here we've got a bridge, here we've got the big truss connecting to the two ladder trusses, we call these, on either side. So even the walls are kind of vertical trusses. And here's the tensile rod that's carrying the floors, isn't it? And there you can look at that inside. This is a nice pin joint connection. Why would you do that? Well, you do it for a couple of reasons. One is that if you had to span the floor from here to here, it would be a very deep section, wouldn't it? It's quite a big span to depth ratio. So it pushes all the building up higher and higher and higher if each floor had to span. Instead, all the spanning, all the load, if you like, is taken back up to the top there, and they're hung from it, which is rather nice. Here's another example of the same kind of thing. So I quite like these as buildings. This is Norman Foster's Hong Kong and Shanghai Bank building in Hong Kong, and again it's exactly the same principle is working here. Apparently this is one of the most expensive buildings in terms of the square meterage per square meter ever built. Might still be. So again, here we have, you can see there's a ladder truss here. It's actually a Vierendeel truss, you can see by the connections, isn't it? There's a number of these on plan, and what's happening every so often there is it's almost like a coat hanger, isn't it? It's a big coat hanger, a larger truss that connects these two. All of these floors, so there's 1, 2, 3, 4, 5, 6 floors, are suspended from the coat hanger at that point there. That's what's making that very thin and very delicate floor load. Okay. And there's some nice detailing that solves the problems of the multitudinous connections in this building. So here's the A-frame, again extruded, repeated, and as I said earlier, the beauty of it as a simple structural form is that it is self-bracing. It's a triangulated form. Why wouldn't you use it? It's very elegant, it's very simple. You have a sloping roof, taking the rain off if you need to. Remember what I said about sloping roofs, those of you that saw that lecture, I can't remember when it was, that you're using gravity to get rid of water, which is sensible. A flat roof requires, if you like, some kind of technology to keep the water off, some material that will stop the transmission of water, but in this case you've always got gravity on your side. So you might think of a pitched roof, we call it pitched, Pitched roof, as a kind of old school traditional form of architecture, but actually there's a lot of sense in it. So here's again traditional, this is called a Cruck frame, C-R-U-K or C-R-U-C-K, I'm not entirely sure. Very traditional, this is an oak timber frame building that you're looking at on the left hand side of the screen here, but it's a series of A-frames. So it's a lovely simple traditional way of putting turning two-dimensional shape into a three-dimensional volume. These are actually concrete columns. This is was the only 50-metre swimming pool in London. It's at Crystal Palace in South London before the Olympics of 2012, when Zaha built her pool out at Stratford. But this, previous to that, this was the only 50-metre pool in London. It's a beautiful building. It's a cathedral. If you do get a chance to go down, it's open to the public. You can go and swim in it. Go to South London and have a look at this astonishingly beautiful building. All cast in situ concrete. Probably 1960s, I suspect. Timber, again, it's not literally an A-frame, but you can understand, you can see the same principles in operation, can't you? This is a relatively new project for a pier, a jetty. Now, I mentioned the portal frame earlier. The only difference here is that it's an A-frame effectively, but it's the depth of this structure. This is actually engineered timber. You can see it's not one. It's not been cut off a log. It's a series of glue laminated timber sections glued together. But the depth that you get here means that the building is effectively triangulated within the structure itself. There is you remember we talked about invisible triangles here, there's another one here. So it's a stiff structure laterally. It will resist any kind of lateral load because of that depth of these elements. There are certain terminology that you use when you're constructing a portal frame. When you go and look at large open plan, shall we say sheds, for want of a better word, all the stuff that Amazon builds, all the stuff that large scale industry needs, you will often be built with these kinds of techniques. There you can see literally the triangulation of the spans of the spanning elements here, can't you? And they're repeated. This is quite an old system. It used to be used for making agricultural barns, and it's concrete. It's a concrete portal frame. Very nice. There's again an engineered timber version of a portal frame. Can you see it's the depth? It's this depth in the section that's allowing it to work as a portal. There's a trussed version of the same. This is a building by Jean Prouvé, P-R-O-U-V-E acute, that I will go into in some detail, but not today. Suffice to say that this is a lovely reproduction of it. This was, you can tell, it was a kind of prefabricated structure. Prouvé was a metal worker, so this is all folded sheet metal. This is not heavy I-sections, steel I-sections or anything like that. It's all folded metal. But can you see that this roof structure, by the way, this whole building was designed to be incredibly lightweight, that you could put the whole thing into the belly of an airplane and ship it around the world. That was the principle. But all the load from the roof is coming down onto these are little portal frames. They look a bit like, anyone who's a musician will know what a tuning fork looks like. They look a little bit like a tuning fork. And so all the load from the roof comes back down to these little portal frames and is stabilized by the thickness of the walls on the outside of the structure. And that's it. That's doing all the work. It's lovely, isn't it, to look at a cross-section here, look at the construction of the cross-section, because you can really understand the structural logic of the building, can't you? So I mentioned earlier that the final part of this, if you like, 2D transferred into 3D way of creating volume, and here's the last one, which is what we call cable stayed structures. This is the Schlumberger Center, SCHLUMBERGER, designed by Michael Hopkins and Partners, HOPKINS. It's actually a kind of research establishment on the outside of Cambridge. If you're going to build structures like this, of course, this is a sort of lightweight tent structure, so there's a fairly solid building on either side at the ground level. Here's the big open plan areas in the middle. Of course, you do need a little bit of space around your building. It's not easy to build these kind of structures in a dense urban situation. But can you see what's going on here? There's actually 1, 2, 3, 4 what you might otherwise think of as cable-stayed bridges, a series of cable-stayed bridges. So you've got masts in pure tension, pure compression, pure tension, pure compression, and these masts are carrying the fabric to create the climatic envelope. Very beautiful structure. There it is again. Another version of the same thing. Well, this is not a fabric structure, this is actually a solid structure. This is a Richard Rogers building in, well, there's two here. This is the one I actually visited, which is the Inmos factory in South Wales. Inmos, they manufacture silicon chips. And look, what they were looking for was a big open plan space. Okay, that was the key to this building. Maybe in the current age, open plan isn't so popular anymore, but anyway, it was at that time. And in order to do it, he's created a mast. This is the central mast here, and he's hanging with cables the trusses from the mast and just repeating that element as a series of, again, that's the two-dimensional shape, that's the cable stay that is then being repeated to create the volume. This, I think, is the technology facility in Princeton, but the same principle occurring, and it's counterbalanced, isn't it? Equal and opposite on either side, a little bit like the cantilevers we looked at earlier on. So that's a lovely way of if you like, creating three-dimensional volumes from delicate, lightweight cable stay structures. This is actually Richard Rogers again, very similar principle going on. This is it was the Renault, the site of a Renault storage facility or parts facility in Swindon. I'm not sure if it is still that, but it is typical of Rogers in a way, because there you can see expressed the structural logic of the building is clearly expressed. But it's a two-dimensional, sort of two-dimensional shape that is just repeated to carry the roof, and that's all it's doing in the end. The key to all this is you're carrying a roof, aren't you? That's all you're doing. And you know this one, you're probably familiar with it. You call it the O2 Arena. As I said, I always thought it never got better than that. It looked like a sort of cloud when it was being built. It was very interesting, very beautiful structure. But as I say, this is the cable stay structure rotated. So in another world, it would be a series of bridges, 6 bridges, wouldn't it, rotated around the center point. Each one of the masts has an equal and opposite on the other side and is pulled back down to ground, remember, with some mass that's counterbalancing the structure. As I said earlier, if you've got the space to come outside the volume, which you need to do with cable stayed structures, it's a very elegant and lightweight way of creating structure. And just to be a little bit frivolous, I did a project at Greenwich University with some students some years ago to try and recreate the O2 Arena, but on a much smaller scale. I think this is only a tenth. This is 10 meters. No, it's 1/36th size, and we decided to do it entirely with timber and rope. In terms of the cost, I think, although it was 1/36th of the size, it was about a millionth of the cost, because it was all timber and rope from our local B&Q. Anyway, you can see fairly clearly from here the principle of these equal and opposite masts, can't you? That are dolphin. Little pin joint here so that they fall into the position they need. There's the mass, in this case just a series of concrete blocks that is providing the mass to balance the whole structure. Does look like it's sort of landed from outer space, doesn't it? So here's a couple of more examples of sort of more sophisticated version of the same thing. That gentleman on the right there is Fry Otto, is a name I've mentioned before, the great pioneer of tensile structures, OTTO. I'm not sure who the other gentlemen are, and that's embarrassing because I probably should. But this is Fry Otto, look, making the physical model of a cable net structure, cable net building, isn't it? Using this repeated series of elements. There's the real thing. Interestingly, they built it. This is at Hook Park in Dorset. It's part of the Architectural Association's. Well, it belongs to the Architectural Association, Hook Park, and they build interesting prototype buildings down there. And this is one of them. And can you see it's actually a series of A-frames, but the A-frames are carrying attention these logs here, which are wanting to fall away, aren't they? They're wanting to fall away, and they've been carried back to these central masts. Rather elegant structure, using local resources, using trees that came from Hook Park. Here's another kind of more grand version of the same thing. So this is Erno Saarinen, the Scandinavian architect. Saarinen, Saarinen, Saarinen. Oh, the Scandinavians amongst you will be so angry with me, but anyway, it's something like that. The same principle you can just about see is going on. So although it's concrete, this is hung, isn't it, from these are big concrete masts on either edge, yes, of course, and they're stiff because they have internal triangulation, don't you? So they're wanting to fall away. They're sort of wanting to fall away, but they have a stiffness and strength because of that depth and their tapering, and they're hanging that reinforced steel, reinforced concrete floor roof between them. So that's again, it's a cable net structure, and that's many architects and engineers think this is one of the most beautiful structures in the world. This is Alvaro Siza, Siza, Portuguese architect. This is the building he designed for the Lisbon Expo towards the end of the last century. You wonder what this is, don't you? You look at that and you go, wow, it's a kind of almost like a sheet of fabric that's hung, but of course it is reinforced concrete. It's reinforced concrete. And you can just about see here that there you can see it, can't you, quite clearly, the steel reinforcing that is connected back to these big shear walls. So instead of having a mast here and it's tied back, as in some of the buildings we've seen, all that work that's resisting the pull of this canopy is done by this series of shear walls here. They're doing the job of resisting the tensile pull of the structure. And here's a lovely engineered timber version of the same relatively recent building, but again you can see here, can't you, here's the concrete sort of semi A-frame concrete masts at one end, and this is engineered timber, relatively lightweight series of glue laminated timber beams. You can just about see a detail here that are hung from one end to the other and flop naturally to take their shapes. So it's a lovely way of lightweight way of putting roofs together. So we get on to the arch now, and it's an important, of course, element in forming three-dimensional shapes from a simple two-dimensional cross section. The reasons for this statement I'm not entirely sure, but we do know engineering wise that certain mathematical curves work efficiently structurally, and they can all be derived from the cone, as you can see here. So sections of a circle, of an ellipse, of a parabola, and of a hyperbola can develop from a cone and are very useful structurally. It's a natural curve. This is what happens if you hose water into the air. It's a natural curve, and of course you can calculate these parabolic curves mathematically. So, as I think I've mentioned a number of times, there is a lovely relationship between geometry and physics, and therefore the shapes that we can achieve structurally. This is called a catenary curve. You may have heard that expression, C-A-T-E-N-A-R-Y. Have I mentioned them? Yes, there it is, the catenary. So this is a curve that develops when you literally hang a rope or string or something that is flexible from 2 points, and they can be eccentric, as shown in the diagram on the right here. The points don't have to be at the same point. But you will develop here from this hanging process a natural curve. If you flip that, if you flip it so that it becomes an arch, it is an efficient structural shape. And here's a little example of it, one of the tallest freestanding arches in the world. This is in I'll get back to you on that. Anyway, a very famous arch that I've completely forgotten the name of. And there's the catenary equation, and there on the right is the graph. It shows how it developed. But that arch is a catenary curve. So if you repeat the arch, simply extrude it and iterate it, you will develop a vault. This is the Science Museum. No, it's not. It's the Natural History Museum. I'm sure a number of you have been there in your lives. I would hope you would hope so. Beautiful, beautiful, beautiful space. What have we got? A series of curved trusses, haven't we? That are doing the work of holding the roof up. Train station in Berlin. This is a Norman Foster. This is an elliptical arch. Series of perforated steel beams doing the job. Simple trusses, curved to form arches, repeated. Slightly more complicated trusses. This happens to be Liverpool Lime Street Station, and look at these beautiful, elegant connecting pieces between the arches. Again, remember, wherever you can reduce load, reduce it. Instead of having one thick member, it's tapering. It's got a series of beautiful connections. I mean, this is not modern. This is an old structure, but it's very beautiful. And remember, we talked about the offset. So this is the roof at the Imperial War Museum in South London. So here we've offset the structure. Don't ignore these, because that's just the glazing curves. But the main structure is this sort of grid, a series of arches, but they've been offset against each other, so that you get a very efficient, stiff roof structure. Here's the same thing happening again. I talk about this a little bit more when we look at timber frames, timber structures next term, but again, it's the same principle in operation. You may have heard the term grid shell applied to these kind of structures. GRID, grid shell structure. So that's a grid shell, that's a grid shell. Yeah. Of course, the Gothic arch, the great use of stone to make arches, is prevalent throughout Europe and various parts of the world, repeating that arch element to carry roofs. And again, as I mentioned earlier, the vault, once you start to rotate it, these are all just repeated, extruded, aren't they? Once you rotate the arch, you suddenly develop some very interesting three-dimensional forms, but it's still working from a simple two-dimensional shape. Wells Cathedral, unbelievably beautiful. But the principle is the arch, and how to manipulate the arch by repeating it to create three-dimensional form. This is called a star vault or a stellar vault at Westminster Abbey. Series of rotated arches. I'm leaving it on the screen for a moment just so that you can take in the astonishing beauty of it. And this is Gaudi doing the same thing in Sagrada Familia in Barcelona. So all of these arches are pure, these are working in pure compression, because we're working here with stone now, aren't we? Stone, as we've said, is a low tensile building material. There is no tensile strength in it. Therefore, everything's in pure compression in these buildings. Here's brick arches by is he Spanish or South American? I can't remember now. Cesar Martinel. Beautiful brick arches doing the same thing. Here they are not rotated, they're repeated in, they're extruded, aren't they? But look at the delicacy of those. Beautiful little brick arches that are carrying the roof structures here. Reinforced concrete doing the same thing. This is at the University of Cambridge. This is one of the halls of residence. Beg your pardon, it's one of the colleges in Cambridge. That's the library. What a beautiful building it is. Mary Edwards College in Cambridge. Of course, the whole thing is designed around natural light, isn't it? But it is a series of arches and vaults in one direction, in two directions in this case. So should mention the Catalan vault because, generally speaking, to make vaults, yes, as we said earlier, you need stone in compression or brick. The interesting thing about the Catalan vault is they're very thin in terms of they're using clay tiles or clay bricks, and you can just about see that this is an example from the Guastavino company, who developed their technique throughout the world, and I think in the 18th century and early 19th century and early 20th century developed this technique. This is actually in New York, and the interesting thing about it is you can see using very thin shell, very thin clay tiles to make these structures. Instead of you're not casting a lump of concrete onto a big negative shape, are you? You just need these guidelines, and you can gradually build the structure up. So it's a very efficient way of putting buildings together. And this is a fairly modern version of it. This was only built fairly recently in Africa, using the same principle, because you can see the timber formwork here is not formwork, as in you're not pouring concrete onto a timber shuttering, are you? It's just giving you the overall geometry, and you can see here, you're gradually building up layer upon layer of these thin bricks or thin tiles to make the structure vault, the arches vault. It's efficient. It's efficient in the actual construction process. It's also efficient in that you're using clay, which is a very common and renewable material throughout the world. You can find it locally, you can bake it, and you can build with it. That's the completed building that we were just looking at. I think it's actually South Africa, this building. These astonishing structures, these are actually also thin clay vaults. Some people would call this structural gymnastics. It's buildings designed by Eladio Dieste, D-I-E-S-T-E, a Uruguayan architect. Again, he's working with clay bricks. There is some tensile reinforcing in these. You could imagine that, isn't there? There's a very thin layers of, almost like chicken wire, in fact, between layers of the clay tiles to make these work. And just to say that, a vault, repeating a two-dimensional arch to create a vaulted structure, it does not have to be uniform, doesn't have to be symmetrical. So this is the work of Knox architects, NOX, Lars Spoybrook, designing a interesting structure. And you can see here that there's a series of arches that are being repeated. So it is theoretically a vaulted structure, but they're not orthogonal and they're not symmetrical. It gives you that possibility. Here's another interesting similar kind of structure where we're using steel trusses. This is a small, fairly lightweight, deployable auditorium structure, but it's a vault. It's a series of arches repeated. And here's a couple of arches repeated. This is, again, funnily enough, this is Hook Park again. We talked about earlier. This is the Architectural Association site in Dorset. And the same principle is happening here, but they're using the materials, aren't they? They're using logs, pretty much as they're found, to make a couple of big arches to carry the roof. It's a vault. It's another vaulted structure. If you rotate the arch, in the simplest terms, you start to develop domes rather than vaults. If you extrude the arch, you develop a vault. If you rotate the arch, you develop a dome. Here we've got a series of, these are actually glue laminated arches, aren't they? Glue laminated ribs. They're connected along the edge, because these elements are almost in pure tension, because they're just stopping the arch from splaying outwards. They're just connecting the ribs together. There's one you're all pretty familiar with, I'm sure. But just to go back to that issue of the arch wanting to kind of explode almost here, even you look in St Paul's, it's locked together here. These are actually chains, and this is the same again. This is a kind of chain system that stops the rotated vault, the arch, from wanting to splay out from the center point. So that's what was happening with just these little connection points here. The Parthenon in Rome, Pantheon in Rome, I should say. Parthenon in Athens, Pantheon in Rome. More buildings in Rome using the same principle, rotating. And yes, that's probably enough for today. To remind you that if you go back and look at the diagram that I showed at the beginning, which I said will be on Blackboard, you can review the different kinds of shapes and forms that can develop three-dimensional volumes from two-dimensional shapes. Thank you very much.